All right, so let's go ahead and do another problem here. So now we want to determine the magnitude and location of the equivalent resultant force acting on this shaft right here based on this distributed load. So we can see here our distributed load is a function of x, so it looks like this, and that is equal to, we have 60 x squared, and this one has units of newtons per meter, which is cool. And for a shape that is a function, to find the resultant force, we just need to find the area underneath this curve. So, which is what we did similarly with the triangle and the rectangles. We just found what the area was under the curve, which was either, a straight line horizontally or a angled line. Then we can find out what the resultant force is. So resultant force is just equal to the total area under the curve. And if we do with the function, we have dFr, because we want to look at, we can see here with calculus, we can remember that when we take the integral under this curve, that is how we can find the area. And what it's doing essentially is it's saying there's these very, very small rectangles that are oriented in this way, and they are of width dx and of height the function. And if we add together all of these different rectangles, that will give us the total area. So we have our resultant force total is going to equal to, which is a small at this little tiny rectangle over this area. So if we want to find the total one, we just do the integral. So we have integral of FR, and this is from our limits. So for this problem here, if we say, oh, this is 0 to here, 2, so our limits will be 0 to 2 of dFr, which is equal to the integral of the area from 2 to 0. But this isn't necessarily something that we can integrate, so we need to figure out what dA is. So what is dA? dA is equal to still a rectangle, length times height, or base times height. So this one here, our length is going to be the width of that, so that's dx. And the height of that is, again, the function. So that's just w of x. So now we can plug this into, substitute it into our equation, and we're going to get now the integral from 0 to 2 df resultant is equal to the integral from 0 to 2 of w of x dx. And this makes sense too of our limits, because this limit is of the x-axis, so we want to make sure that our function is in the terms of x. Okay, so this one here ends up getting us the resultant force is then equal to the integral from 0 to 2 of, what's our function again, 60x squared dx. Okay, and so when we integrate that, we end up getting here 60 divided by 3, x to the power 3 from 0 to 2. And this one here, if we simplify it, we're going to get 22 to the power of 3 minus 20 times 0 to the power of 3. That's how you do integration. And our results end up being 160 newtons, and this is the resultant force. And if this was a vector, we know that it's going down because that's the direction of the distributed force. So then this would be negative 160 newtons in the j direction. All right, and that's how you do the resultant force, but now we need to locate where that resultant force is. And when we locate it, that was our x bar. I'm going to put it over here on this side. So I'll also write step 2, find FR location, x bar. So here, our equation there is going to be the integral over the area. We have x, w, x, dx, divided by our resultant force, which is this one. And we already know what this one is because we calculated that right here, so we can just plug that in. And we end up getting x bar is then from 0 to 2, the integral of x multiplied by our function, which was 60 x squared dx, divided by 160, and this is just the magnitude there. And so here we need to go and simplify that. So we got 0 to 2 of 60 x cubed dx divided by the 160 there. And our integration, we end up getting our result here of, we get 60 over 160 times it by 1 over 4, x to the power 4, from 0 to 2, and when you calculate all this, it ends up being 1.5 meters there. So again, just as a reminder that this equation here, what it's representing is the resultant moment, and we're finding our distance based off of our moment equation. So we have moment is equal to our moment arm multiplied by a resultant force. This is the resultant moment. So what we're doing is we're finding out what our moment arm is by doing our moment, which is m r divided by f r. All right, and then now the last thing to do is just to check our answer to see, does this make sense? 1.5, so that would be located right here, as we can see in this diagram. And we can see that this is probably proportionate for what's on this side of the resultant force to this side. So I would say that this value would make sense there. All right, and that's how you just do distributed loads with a function.